Hello, this is the course of data mining, and in this video I would like to discuss about the similarity and distance. Some literatures they mention similarity and dissimilarity. Yeah, we can also use this terminology for our course. So what is similarity and what is dissimilarity? The similarity refers to a numerical measure of how alike two data objects. So when you are dealing with data object, if you still remember, okay, two data object means if you are having a kind of table, okay. So if you have table, so the column means the attributes, and the row means the object. Okay. Now, I would like to compare between the first row and the second row. Then, in this case, if like say yeah, you have the data here, you want to compare with this data. If you want to, if you have this data, you want to compare with this data. So the comparison between two data objects, you can refer to the previous video about what is the object. Value is higher when objects are more alike. Okay. So this similarity, the value will be high if two objects are similar. Okay. Then often falls in the range of 0, 1. What about the dissimilarity? The dissimilarity is having another name, which is distance. It is a numerical measure of how different two data objects are. So the goal are different. If we want to use the similarity, we want to know how alike two data. If we want to see the distance, we want to see how different two data. Okay. So the keyword is the how alike, and this one how different. Lower when objects are more alike. So the value should be lower if two objects are more similar. Minimum dissimilarity is often 0 and upper limit varies. So the upper limit can be more than 1. So it can be 5, it can be 10, and etc. In other literatures, they mention as proximity. So proximity refers to a similarity or dissimilarity. So it depends on the context that you want to apply the concept of proximity. In the case of the metrics, okay, so we are using the data metrics and dissimilarity metrics. The data matrix, it contains of n data points with p dimensions. So p dimension means the p means the column. Okay, I have the p column, so it is the p dimension, and I have the n data point. So we have what the number of row will be n. Okay. So in the term of data matrix, we have two modes. Okay. So the mode of data point and the dimension. However, we can also see the case in the dissimilarity matrix. In the dissimilarity matrix, we have n data points and we register only the distance. So if I want to know the distance between the point 2 and 1, so the result will be here, there is the distance, and the distance here, actually it is the same with this one. So it's like the, yeah, it's like the mirror, okay? And because we can say that the distance is the same, so we just use the triangular matrix. Okay, what is the meaning by the triangular matrix? Yeah, we can say that the triangular matrix is something related to the triangular, and this triangular is, yeah, we have this one. So the data will be only in this triangle. Yeah, there will be no other data in the upper side of the triangle. We call this a single mode. Okay, because we want to see the relationship between the two data points, and yeah, we just use only one. Yes. Okay, let's suppose we have the attribute. We know the attribute of our data, and let's say if we want to deal with the nominal attributes. Do you still remember what is nominal? Okay, let's say I have uh, two or more states, so yellow, red, blue, green, and yeah, it can be the generalization of the binary attribute. We can have two methods. Okay, the first method is simple matching. Okay, we have the first is simple matching, and the second method is use a large number of binary attributes. Let's see. In the simple matching, we have M, which is the number of matches, and P is the number of variables. And the formula will be here. To measure the T between I and J, the formula will be P minus M divided by P. Okay, let's see. I have two data, okay, the person 1 and person 2. And there are 4 attributes: shirt, pants, shoes, and hat. Okay, so how many attributes do we have? How many variables do we have? Yeah, there are 4. Okay, now I would like to know how many data that are matches. Okay, let's see. The person 1 used the red shirt and the person 2 used blue shirt, so it's not same. Okay, how about pants? The person 1 used black pants and the person 2 used black pants. Oh, okay, so they are match. Okay, what about shoes? White shoes, white shoes. Okay, they are match. Okay, what about hat? Yellow, orange, so they do not match. Then the number of matches equals to 2. Okay, now how we can apply to the formula? We can see P is total variables and M is the total matches. So we have 4 minus 2 divided by P. P is the 4. Okay, so it means we have 2 divided by 4. Then the result will be half. So the distance or the proximity measure equals to half. Okay, if we want to use the second method, it means we will use a large number of binary attributes. So we need to convert the nominal attributes into binary. How? Let's see. So we have the same data. Okay? We have the same data here, and then we want to change this into the binary attributes. It's not that easy, but it's also not that difficult to understand this one. Let's say if I have the data, the nominal attribute like this, so I can just put the red. Okay, I have red shirt for person 1. Then okay, I can say this is 1. Okay, so the person 1 shirt red. Okay, red shirt. Yes, it is 1. But what about person 2? Because the person 2 used blue shirt, so the value will be 0. What about shirt blue? Because the person 2 is now wearing blue shirt, then I put this is 1, and the person 1 will be 0. Okay, and so on. So the pants black is 1, 1. The shoes white is 1 and 1. Hat yellow, it is 1 for person 1, but 0 for the person 2. Hat orange, it is 0 for the person 1 and 1 for the person 2. So using this kind of binary attributes, we can use this measure. Okay, we can use what we call as the contingency table. Okay, so the contingency table for binary data, it consists of 4 items. Okay, Q, R, S, and T. Okay, if the object I is 1 and the object J is 1, then yeah, we want to know how many items. So in this case, how many? There is 1 and 1. Okay, there's 1 and there is 2. Okay, then I can say if we have this kind of object for the first one, then we can have like okay, so we can have this one 1 0, and then this is also 1 0. So the number 1 and 1, object I1 and the other object is 1, there are 2. What about 1 0 0 1? Okay, so 1 0 1 0, so there are 2. So there are 1 0 1 0, there are 2, and then 0 1 0 1, there are 2. Okay, and then this one 0. Then from this one we can measure the q plus r, s plus t, q plus s, r plus t, and then we can get the p. P is the number of variables. If we want to measure the symmetric binary variables, do you still remember what is symmetric? Yeah. Okay, symmetric means the two binary variables are the same. They are having the same importance. But for the asymmetric binary variables, one of the variables is more important than the other. For example, you still remember about the HIV. When you got the test of HIV, positive is more important for the hospital or for the patient. And also for COVID-19 now, yeah, when you take a test, then the negative will be more important for you. Yeah. So the formula is different. If we have the symmetric, we can just use the R plus S, okay? R plus S divided by Q plus R plus S plus T. But if it is an asymmetric binary, okay, if it is an asymmetric binary, then it is R plus S divided by Q plus R plus S. There is another method, we call it the Jaccard coefficient. So the Jaccard coefficient, we use the Q divided by Q plus R plus S. Now let's see this example. Yeah, this is the dissimilarity between binary variables, and we want to measure the distance for asymmetric binary variables. Okay, asymmetric. You know that gender is symmetric, so let's just omit the gender. What about the remaining attributes? The remaining attributes are asymmetric. Okay, so this we will not see this gender. Okay, instead we use fever, cough, test 1, test 2, test 3, test 4. So this is a kind of test in the hospital, and you want to know the similarity between Jack and Mary. What is it? Before we continue, we need to understand the Y and P. So if the fever Y means there is a fever, okay. N means no, okay. Oh, sorry, N means negative, P means positive, okay. Now we have Y and P equals to 1 and the value of N equals to 0. So if you want to compare Jack and Mary, the result will be, okay, so if you check this one, the QRST, okay, and the formula will be R plus S divided by Q plus R plus S, okay. So if I can draw again, so we have the this is the object 1 0, and then this is object 1 0. Okay, now if the, let's say the first Jack and Mary, for Jack, Mary, Y and Y, okay, Y means 1 and 1, okay, there's 1. And then what about this N and N? Okay, so 0 and 0, so there's 1. And what about the P and P? Okay, 1 and 1, so there are 2. And then N and N, okay, there are 2. Okay, and then N plus P, okay, N means the 0, and then P is 1, 0 and 1, so there's 1. And then the N and N, okay, so there are 3. Okay, so I can just say that this is the I can just put the, this is 2, and this is 3, okay, and then this is 1. And the result here is, yeah, this is R plus S. What is R? R is 0, okay, and then S is 1, so 0 plus 1 divided by Q. Q is 2 plus 0, 0 is R, and plus the T, which is 1. And the result is 0.33. What about Jack and Jim? Okay, let's see, Jack and Jim. So we have the same, we need to build the contingency table, okay. So with this contingency table, let's see, we have 1 and then 0, we have 1 and 0, and the respective of Jack will be the first. So the Jack, okay, Y and Y. So we have 1, okay, and then Y, N and P. So 0 and 1. So we have 1, and then we have P and N. Okay, P is 1 and N is 0. So we have 1, and we have N and N. So we have 1 and N. We have 1 and N. Okay. So at the final, we have this one as 3 and the other are 1. And after we have this, we can calculate again the same. So we have 1, 1, 1. So 1 plus 1, it is the R, and this is the S. And the Q is 1, and then S is 1, and R is 1. So the result is this one. Can you calculate by your own for Jim and Mary? Okay, so you can try. In the case of the numerical data, okay, in the numerical data, usually there is kind of gap. Okay? So some data has gap, and in order to minimize the gap, we can use the standardization. So the standardization measure is one of the good measure is the Z-score. Okay, I don't know. Oh, okay. When we deal with the Z-score, this is the formula. The X is the raw data, okay, and mu is the mean of population, and tau is the standard deviation. And we want to measure the distance between the raw score and the population mean in the unit of the standard deviation. And for every negative, when the raw score is below the mean, then we need just give the plus. Okay. Usually, we before we do the Z-score, we need to calculate the mean and the sigma. Okay, the sigma tau. Okay, the sigma is the variance, the standard deviation, and there is another way, which is using the mean absolute deviation. So in the mean absolute deviation, this is the formula. Okay, so the 1 divided by n multiplied by x1f minus mf. So mf is the average. So this 1 divided by n multiplied by x1, x2, xn, and so on. In order to get the standardized measure, we used almost the same Z value with the Z-score, but now we are having a different way to get the S, the SF. The SF is different. Usually, using the mean absolute deviation is more robust than standard deviation. Let's see. Yeah, this is just one very simple example. If you have the data 90, 75, 85, 180. So the total will be 430, and the mean will be 86. And in order to measure the standard deviation, you need to find the gap between the real value and the mean, and then you will just give the power of 2. The result will be 16, and that's 121, and then 1, and then 196, and then 36 for all the data. So every data should be minus with the mean and then make a square. The result of the square root, so if you sum all this number, the result will be 370, And because we have 5 data, just divide by 5, and then we use the square root. So the square root is this one, okay? And we get the standard deviation is 8.6. After we have this 8.6, so we just fit for every data. So we have the set 1. The data 1 is 90. So 90 minus the mean, the mu, and then divided by the standard deviation, which is 8.6. So 8.6 is from here, and the mu, the 86, is from here. So we can get the value is about 0.46. So it's the same. You can just calculate the remaining value. If we are dealing with the MAD, okay, the MAD is just to find the absolute value, 90 minus 86. So the result is 4. 75 minus 86, yeah, because it is minus, yeah, we put the absolute and the result will be positive, 11, and so on. After we get all the numbers, we just plus, and we make the summation and then divide it by the total data, which is the result is 7.2. The same with the example in the Z-score. So we want to put the Z1, Z2, Z3, and so on. And for every data, 90 minus 86 is the mu, and then we divide with the standard deviation from MAD, which is 72. Oh, sorry, 7.2. And after you do this operation, yeah, you will get this number. Okay, 4 divided by 7.2 minus 11 divided by 7.2, and so on. And yeah, the case in the data matrix and the dissimilarity matrix, actually, what you want to get to the dissimilarity matrix, it is obtained from the data matrix. So we have this data matrix, and this data matrix is the result. The dissimilarity matrix is the result from this data matrix. Okay. Now, what is the good measure for distance or the dissimilarity? There's one tools we call, there's one algorithm. This is a very popular. We call it Minkowski distance. Okay, so this Minkowski distance is the this Minkowski distance is using this formula. So this formula is the general general distance measures. And when we have the eights, okay, you can see later the eights. We have I is the first data, and J is the second data. Okay, so we have the two p-dimensional object. And whenever we have the eights, it is the order, and you know, we can say the formula later is L its norm. So when we have the L its norm like this, okay, later we will see the formula again. So the properties here, if we are dealing with the proximity, okay, there will be 3 properties. Dij should be greater than 0. Okay, it should be positive, and Dij equals to Dgi. Okay, so that's why in the dissimilarity matrix we just have the triangular matrix, and Dij is less than Dik plus Dkj. Okay. So for example, this figure, okay, the I to j, there's a distance, and the distance should be lower than or equal to the Dik and Dkj. So a distance that satisfies this property is a metric. Okay, so you have the metrics for this one. Now, the special cases of the Minkowski distance is, yeah, there are 3 things. So the first is the h equal to 1. Okay, what does it mean by h equal to 1? We just put the h here equals to 1, and yeah, we call the name as the Manhattan distance or L1 norm. The other name of this algorithm is called the Hamming distance. The Hamming distance is the number of bits that are different between 2 binary factors. So we want to find a gap between xi and xj in the first data. We want to find the xi and the xj in the second data, and so on until p. And every subtraction, we will put the absolute function. So the result will be the dij. And these are the second norm. We call it the L2 norm, or Euclidean distance, and the h equals to 2. So I guess it is a very famous formula using the Euclidean distance. So every time we find the gap or the subtraction, we will do the absolute and power of 2. The result will be the square root. Okay, so we put the square root. The number 3 of the Minkowski distance, we use the h equal to infinite. It means is the L max norm or L infinite norm. Okay. This is the maximum difference between any component or attribute of the vector. So we just put the maximum for every number. Now let's see. If you want to measure the Manhattan, okay, I have the x2 and x1. Okay, x1 and x2, and how can we get 5? Okay, how can we get 5? So if you refer to the formula, this one is 3 minus 1. Okay, 3 minus 1, and then you will put the absolute plus, what is it, 2 minus 5. Okay, I mean, maybe if I just make it with the bigger one, 5 minus 2, and then you put the absolute. So the result here is 2 plus 3. Okay, and the distance between object 1 and object 2 is 5. What about the Euclidean distance? In the Euclidean distance, you have the square root. Okay, what is the square root? The square root between the two data. So we want to find the 3 minus 1. 3 minus 1 is 2, and then we want to make it square, power of 2, and then 5 minus 2, which is 3. So okay, 3 power of 2. So the result is the square root of 9, 4 plus 9. Okay, and the power, the square root of 13. So if you check on the calculator, the result will be 3.61. Okay. What about the supremum? In the supremum, how can we get 3? Yeah, we just want to compare between 3 minus 1. Okay, 3 minus 1 is 2. Okay. What about the other attribute? This is 5 divided 5 subtraction by 2. Then the result is 3. Okay. Between 2 and 3, what is the maximum? Of course, 3. So the distance with the supremum is 3. Okay. There is another kind of measures. We call it cosine similarity. In the cosine similarity, it usually refers to the document. As we already learned from the previous video, a document can be represented by thousands of attributes, okay? And each of the recording of the frequency, it means the number of the term in the document. So let's see if we have theme. There are 5 in document 1, 3 in the document 2, and 0 in the document 3, and 0 in the document 4. And you can see the other terms might appear in the document. There can be other vector objects, okay? So gene features in microarrays and etc. So some application is in the information retrieval. You can use in the biological stuff, biologic taxonomy, or gene feature mapping. The cosine measure is the D1 and D2. If there are 2 factors or the term frequency factors, then we can use this one, this formula. Okay, instead of explaining this formula, let's do the example. I want to know the distance between the I want to know the distance between, okay, let's say this document. Yeah, this is from the same data from the previous page. I want to find the similarity between the document 1 and the document 2. So we will use the T. T, what is T? It is referring to the document. So we have 5, 0, 3, 0, 2, and so on. So we just put 5, 0, 3, 0, 2, 2, 0, 0, 0, 2, 0, 0. And what about document 2? Yeah, the same, 3, 0, 2, 0, and so on. And after we have this, we want to multiply between those two numbers. So 5 multiplied by 3 plus 0 multiplied by 0 plus 3 multiplied by 2 and plus 0 multiplied by 0 plus and so on. So you will get this formula. Okay, and the result is 25. After you have this one, we want to get the Euclidean distance of the T1. So the two lines vertical, okay, this one, in many mathematical formulation or in any papers, in any research paper, they just use these two vertical line as the L2 norm. Okay, if you remember from the previous slide, we have learned about the L2 norm. So it is the Euclidean distance. In order to measure the T1, then yeah, we just want to compare with that particular value. So if there is 5, then yeah, we just make 5 multiplied by 5. If it is 0, 0 multiplied by 0. If it is 3, 3 multiplied by 3, and so on. So we just do the calculation until the end of the document. And the document 2 is the same. We have this value, so we just multiply with that individual number. So 3 multiplied by 3 plus 0 multiplied by 3, 0, and so on. And then what is this? The power of 0.5. It means the square root. Okay, so the square root of 42, it refers to 6.8481. And the other one is the square root of 17, and the result is 4.12. Okay, now you have those values, and how can we get the cosine similarity? So the cosine similarity from D1 and D2 equals to 0.94. Wow. How? Yeah, we need to use this formula. So we have the D1 dot D2. So it means the multiplication between every element of those two documents. And then we have the L norm. We want to know the L norm of D1, and then we want to multiply with the L norm of D2. Okay, so the result will be the cosine similarity. Okay, so that's all I think for this video. Now my question is, can you mention the difference between similarity and dissimilarity? Okay, and how many are there for the special cases of Minkowski distance? Okay, so you can answer that one, and please keep on your mind about those kind of learning check, because then there might be some possibility to choose randomly among those questions in your exam. Okay, so thank you very much for joining this video, and I hope to meet you in other video. Thank you very much.